Good afternoon and welcome to today's edition of the joint astronomical colloquium here in Heidelberg. With great pleasure, I welcome Richard Tuffs from the Max Planck Institute for Nuclear Physics here in Heidelberg, who has been here many years. Let me say a few words about the speaker. He got his PhD in Cambridge, UK in 1984. Then he worked for 2 years for the British Antarctic Survey, which sounds like a really cool working environment. From that, he moved to a slightly more moderate climate. He moved to Bonn to work at the Max Planck Institute for Radio Astronomy. He also moved up in frequency space. He worked on dust and submillimeter at that time. Then he was hired here in Heidelberg at the Max Planck Institute for Nuclear Physics to work for the ISO satellite, who observed in the submillimeter near-infrared wavelengths. For many years, got very interesting results, and he's now slowly progressing to shorter wavelengths. He will talk about what we can learn about the growth of spiral galaxies over cosmic time from the infrared to gamma rays, and we will learn how the infrared and gamma ray emission is closely connected to say more about dust in the interstellar medium and the star formation process in galaxies. So let us welcome Richard.
Thank you very much, Ralph. Thank you. Well, it is an extraordinary privilege to have been able to work here in Heidelberg for these decades. And it's a great pleasure to be able to give this talk, most particularly because it gives me a chance to thank the many colleagues in the Max Planck Institute for Nuclear Physics, in particular in the Infrared Astrophysics group, which is a little group which grew out of the work on the Infrared Space Observatory. What am I doing?
We're looking at the
right. All right. And I would like to extend my very personal and deep gratitude to Heinrich Volk, who initiated our involvement in that project, and for all his support over the years in the work we've been doing. And I'll be talking about some of the more recent developments of work which started back then in this talk. And I'd also like, in particular, to thank my colleagues, Christina Popescu, who's done a lot of the work which I'll be presenting, in particular on the radiation transfer analysis of propagation of light in spiral galaxies, which is central to the physics which I'll be describing. Jörg Fischerer, who is was behind all the very intricate dust emission physics and software routines which we built into our radiation transfer analysis. And more recently, Mayat Grutis, who was an IMPRES scholar here for 3.5 years, and a postdoc for another year, who did a lot of very specific work I'll be describing about the growth of spiral galaxies. And during this time, I've had the pleasure to work with many collaborators, and I would like also to give my heartfelt thanks to them too for all the pleasurable times we've had together. And lastly, this talk will be using a lot of data from the Galaxian Mass Assembly team. My thanks to them, and let's go. I should just say that we're not actually at the stage where we're able to look at Z1 galaxies in gamma rays. We hope to be there sometime during the next century. But what I will be doing is to talk about a theme which is a sort of recurring theme on and off during my time as a scientist, which is the link between the dark matter distribution. Here you see the Millennium Survey of a redshift of about 0.1, and the observations of the galaxy population. And of course, you're looking at chalk and cheese. This is dark matter, whatever that is, and this is primarily stars. And I'm going to be talking about what we know about what the connection between these objects and these objects is. And if I might just introduce this topic by saying that the galaxies in the universe out to redshifts of order 4 formed most of the stars, particularly between redshifts 2 and 4, and that star formation is now generally accepted to have occurred in primarily in rotationally supported secular evolving disks. And I'm going to give one or two pieces of evidence about that. One is recent observations of spectroscopic cubes of galaxies. This was a set of galaxies. Simply, they took the brightest galaxies, which for this field, being such a small field, the Hubble Ultra Deep Field, which was on the previous overlay, is basically these are galaxies in the range 0.2 to of order redshift 1 for the nearest brightest galaxies in that field. Of course, the field goes out to galaxies beyond redshift 6. But when you look, you see that the rotational disks are all in place at this epoch. Even in this case, spiral arms didn't actually come in until fairly recently, but disk galaxies have been around basically since almost the first stars have formed in your universe. Recent observations with infrared telescopes, infrared spectroscopy in the C2 line and CO lines have also demonstrated the presence of rotating disks of prodigiously forming stars at redshifts of 6. So, another piece of evidence, moving on to that, of course, moving a little bit further out, you can no longer do spectral cubes of galaxies. What you can do is look at their morphologies. And again, these are galaxies which were classified by doing Circic surface photometry by these authors, Cameron and Driver. And this is the Circic index. So on the left here, 0 is basically in a disk, and a bulge or a spheroid is beyond about 0.5. And you've got the color going up here, so you've got blue and red. And what you see, and overlaid here is a local universe sample, and you see that there's two populations in the local universe, blue galaxies, red galaxies, and the red galaxies are predominantly, not all, but predominantly spheroidal, and the blue galaxies are disk-like. And they then did that going backwards in time in the HUDF, and effectively the result is the HUDF galaxies, the brightest ones of all are plotted, are that the blue sequence has formed, and it was present throughout this sequence, but the red sequence basically was not there. It's fairly recent occurrence. So the stars have been forming in this blue sequence with a similar, in objects with a similar morphology, rotationally supported disks, as you see in the current day. But of course, they've not been forming stars at the same rate. What one sees, if one goes back in redshift, this is the famous Nadal plot. I think it's called something else, but anyway, I use the word Nadal. You see this point at the peak of the star formation history of the universe around redshift 2. And you also see that there's roughly equal light given out in UV and infrared. And infrared is light, which is starlight predominantly, which has been absorbed by dust grains in the galaxies. At these redshifts, this light is predominantly UV light, which is absorbed by the grains and re-radiated infrared. And so you do need infrared telescopes to actually measure the star formation out, particularly at these large epochs where there's so much star formation, so much gas in the galaxy that they are somewhat more opaque than local galaxies, not hugely more opaque because they've got a different geometry, but somewhat more opaque. And then the next step in this is to look at the dependence on stellar mass of star formation rates of all these rotationally supported disks. And this is the famous so-called main sequence relation of star-forming galaxies. People don't like the word main sequence. The main sequence means choose something by color. But I'm going to use that as a sort of, in this talk, as a sort of a quick way of describing this relation between star formation rate and solar and stellar mass in these galaxies. And here you see the relation, which is almost linear, not quite linear, at around redshift 1. And then you see the relation at redshift 0 down here. And the blue points are the star-forming galaxies, the red points are the non-star forming galaxies. And as we saw before, this is the blue and red sequence, and these things tend to be spheroids, and the blue ones are disks. And you can also then look at how the position of this line varies with the epoch. It sort of shifts as you come down from redshift like this, and that's the sequence you see here, redshift 4 to redshift 0.25. I'll be showing you results on this later for the local universe at z.1. So that's a summary of all I've just said. I don't need to repeat that all, but the question is, what is the relation of this star formation activity to the dark matter, which is actually on megaparsec scales? And the question really is, how does a star formation in a galaxy depend on where it finds itself within this cosmic web, which is an environment on the megaparsec scales, and does that affect how it forms stars? The answer is maybe, but the point is it a thermodynamic effect that's affecting the intergalactic medium in that dark matter distribution, which is preventing gas reaching stars to form to give the fuel to form those stars? Or is it something to do with, for example, morphological transformations and some local property in galaxies, which means that you need a rotationally supported disk to support star formation, or you simply cannot support so much star formation in a pressure-supported object like a spheroid? And that's the question we're going to be answering. Now, I said that maybe the environment has an effect on star formation in galaxies. Of course, there's a long-known relation between the rate at which stars form and the color of galaxies and the density of the environment they find themselves. Now, this is work by the Cosmos Survey, Nick Scoville's team, where density is parameterized in a three-dimensional photometric redshift survey by the number of galaxies within a volume around each galaxy, and then you look at the ratio between the time taken to form stars and the cosmic timescale. So if this is large, it means it's not forming many stars. So quiescent galaxies are up there, non-quiescent are down there. And for each of these redshift bins in the Cosmos Survey, one can look at all the galaxies and see if there's a relation between the position on the x-axis and the y-axis. So density goes up here, that's high density. And what you see is, if you look at actually I've forgotten what this is. Maturity, yes. So you see that I've forgotten what those two plots are actually. No, sorry, density is not plotted here. This is the mass of a galaxy, that's it. It's the mass of a galaxy versus the star formation activity. And this is galaxies in a high density environment, this is galaxies in a low environment. And the galaxies in the high density environment have this red dead tail coming up. And you see this at all these redshifts. But the point is this because of thermodynamics, or is it because of the different morphologies of galaxies, or something else that I'm not clever enough to think about? That's the same story at higher redshift, although the effect, as we've already seen with the work by Cameron and Driver, is less pronounced at the very high redshifts. And what is this thermodynamic effect which I've referred to? Well, the idea is that gas, this is the virial radius of a dark matter halo, and we've got a disk galaxy in the middle of this halo, and the idea is that the gas that goes eventually into stars in this disk fall in through the virial radius, they get heated, and then they either thermalize if their cooling timescale of that gas is longer than the free timescale, in which you have a hydrostatically supported intergalactic medium within this megaparsec halo, and that's the case down here with a massive halo, and massive halos give you hot gas. Hot gas doesn't cool as well as cold gas. Or if you've got a low mass halo, then the gas essentially falls straight through onto the galaxy. It doesn't actually do that, but that is the process at large scales, at least here. And the point is that there is a sort of critical halo mass, M dark matter halo, of about 10 to the 12 solar masses, where this pressure support really becomes dominant over the free fall. And so for these large halos, which are in high density regions of the universe, you expect less gas coming onto the galaxy because it's pressure supported in the parent halo than in low density halos. And so this would qualitatively explain the cosmological results and what has been seen, the red in high densities. And just to explain this a little bit further, what one see here, this is a T33, which goes as density to the -12. This is the cooling, which timescale, which goes as 1 over density. So what you see here is the cooling curve, the ratio between the relation of temperature and density, and these lines are where those two things equal, and they actually have the property of just going almost parallel to this boundary, which is the boundary between virialized halos and free fall halos. And so that's where this mass comes from. And what you notice is that over all the redshifts, where these lines coming across here, it's around the same critical halo mass. So galaxy evolution somehow has stuck to its same reference halo mass over the cosmic time in the HUDF. Now, I've talked about gas flows coming through the halo, and I'd like to spend 2 or 3 minutes on this overlay, because this is a sort of vocabulary which I'll be using later when I'm going to talk about more complex results from the GAMA survey. By the way, GAMA is gamma and mass assembly. Now I understand why you thought this was a gamma astronomy. This is an optical spectroscopic survey. And so the basic point is that the change in time of the gas mass in the interstellar medium, this is gas mass, is the difference between the radiative stuff coming in and the process for that I've just described on the previous slide, and some mass going out, which is a galactic wind driven by something in the disk of the galaxies. It could be photons, it could be cosmic ray production, it could be some sort of heat produced by an AGN or whatever. That's not clear. But another place the gas goes into the star. So this is just a steady state relation, instantaneous relation between these time derivatives of these masses. And unfortunately, even in the local universe, we can't see the actual gas in these galaxies. So we have to actually have an empirical reference for that. And what we do is use the relation between star formation rate and mass of interstellar medium, or surface densities of those quantities, which is, for example, the Schmidt-Kennicott relation, which we heard a little bit about last week. And if you do that, then you can express all these quantities in terms of star formation rates and different timescales. This timescale T resonance is the time a particle in interstellar medium is able to reside before it gets ejected in a wind. And this is the star formation rate. Now, in a steady state, this goes to 0. So for a steady state, you have star formation rate simply proportional to the inflow. And the point about this equation is that this is all galactic specific quantities. It boils down to a composite timescale, which is this. This is this resonance timescale for the wind. The timescale, the gas particle, the probability gas particle forms a star in the galaxy, and it's like this. And then you can equate this m dot in another equation to the gas coming through the top of the dark matter halo. And of course, that's not necessarily an equality, because, as we have said, gas coming into the top of the dark matter halo, especially in heavy halos, doesn't reach the galaxy, or it has a low probability of reaching the galaxy. And that is described by this function zeta, which I'll be talking about. And zeta is the efficiency by which an intergalactic medium gas particle which passes through the virial shock passes into the interstellar medium of the galaxy. And then you can put this together with this to get one equation. Star formation rate is equal to these quantities, tau, kappa, which are galaxy-specific quantities, zeta, which is an IGM-specific quantity, and that's what we want to find out about, because we want to answer the question, is it something to do with the IGM, which is causing galaxies not to form stars? And the total mass accretion rate of baryons onto the halo, which you can describe as some fixed fraction to the dark matter halo rate. And the idea is you know what the dark matter growth rate is because of those beautiful simulations which Volker Springel and others have been doing in Galaxies and also Heidelberg. And therefore, you ought to be able to, by looking at star formation and something which tells you what the halo mass is, be able to describe what the physics of these parameters is. And so, as I said, if the Coulomb time period is short, this is always perfect efficiency 1. And if the Coulomb time scale is, sorry, that's the other way around, it should be greater, then it's some function of mass halo which is less than 1. And the question is, what is that functional form? Now, the last point to make on this is that if there is exponential growth, then m dot halo is proportional to m halo. And if that's the case, if zeta is proportional to m halo to the -1, the m halo to the -1 cancels out with the m halo, and star formation is completely independent of environment. And it's that issue which we're now going to use the gamma data to investigate. Now, of course, this has been investigated thoroughly before in a different way, namely by the process of abundance matching, which basically is to take all this a priori information about dark matter halos in the universe and their growth rate, and the rate they collide, and the rate in which they sort of go away through tidal effects and whatever you have, and you just basically say over cosmic time what the ratio, what the occupancy of those halos is in terms of stellar mass in galaxies. You also have to specify things like mass functions of galaxies and all that, and then and then what you do is simply look at how the star formation rate over cosmic time is reproduced, because if you specify the function of mass in a halo over z, you can therefore specify how the star formation rate of that galaxy is, and compare it with observations and optimize to get these distributions of m star over m halo. And when you do that, you get this for m star over m halo, and this for this zeta function, which I've just been talking about, lo and behold, wonderful, agrees with the theoretical prediction. It peaks at halo mass, and it peaks at about 10%. And this is the The black curve is the zeta curve. And so it goes down steeply, but not inversely linearly, not as a reciprocal, somewhat more steeply than that in this work. So, the problem with this is that you've made no reference to galaxy physics, galaxy morphology. You also are very insensitive to galaxies which don't happen to be near the peak of this efficiency. You know, the low mass galaxies, in particular, are not well represented by this analysis. And because of this, and because of it's a sort of important thing, we undertook, and the other thing is that they don't actually measure dark matter. So we undertook to look at what zeta is by actually measuring the dark matter distribution in the universe. And that's where the GAMA survey, Galaxy and Mass Assembly, which is color-coded in orange, comes in. This is a bird's eye view on an array versus redshift going in this direction of 300,000 galaxies in the GAMA survey spread over 5 fields. And what you see beautifully, quite clearly, is the cosmic web. And there's other redshift surveys which are also put on for comparison. For our purposes, GAMA has the right mix of depth and redshift and area to be able to do this investigation. And if you look more closely at the cosmic web, a number of papers have been done. This one's by Eardley and John Peacock. One can classify all the structure in the web, voids and 2D things, 1D things, filaments, and the 3D things, the knots. And that's color-coded on these plots, and beautiful, beautiful tomographic representation of the cosmic web. Of course, it's not really the cosmic web. This is the galaxies in the cosmic web. We still want to find out what the real relation is between those quantities. But I'm going to be talking about galaxies in the knots, because that is the extreme density contrast that you see in the universe. And if you want to see how galaxy evolution depends on environment and those density contrasts, that's the place to look. And to quantify the dark matter in those, we use the spectroscopic survey. We look at galaxies which are grouped together in galaxy groups. We look at the velocity dispersions. And we can then use the velocity dispersion to get a first estimate for a mass contained in the group, including all the baryons and all the dark matter. And this is an example of galaxy groups. About half the 300,000 gamma galaxies are grouped together, so there's a lot of particles to measure the dynamics. And this is the number of galaxies in the groups. So you go up to fairly large cluster-sized objects, 10 to the 14, down to things below 10 to the 12 here. And you see beautifully how the filaments are mapped out, and this is color-coded according to the velocity dispersion. So this is 10 to the 14, and this is down to 10 to the 11 or so. And the other reason that this gamma is great for this is because it lies just in front of the kids' photometric survey, weak lending survey. So the redshift of the kids is in this line, the redshift distribution of gamma. So you see that the gamma galaxies and the objects in the web in which they are situated are ideal for investigating through direct measurement through weak lensing analysis. And that analysis actually gives you, when you stack up all those galaxy groups, which I've just told you about, and you do, and then you do a weak lensing analysis, you can get beautiful plots of the typical mass profile in these groups, and also you can actually check independently whether your spectroscopic dynamical masses really are measuring the total mass or not. And so we are actually doing pretty well. I just want to mention something else. This is the distribution of the masses, which is important. And the work we're doing is concentrated below 0.12 in redshift. And the distribution of group masses that you have at that redshift is given by this here. And so what you see is it just goes down sort of to 10 to the 12, but primarily we're going up from this magic mass 10 to the 12 upwards. And that's where we're going to determine zeta. So, to determine zeta, you also need star formation rates, and that's another strength of gamma, because we have wonderful coverage of all the bands needed to completely characterize young stars, stars of any age, plus all the dust, which is absorbing starlight and re-emitting it in the infrared. And there was a concerted observation campaigns done throughout this. The one our institute was involved in was the Galaxies campaign. We even had to negotiate with Caltech to do that, and actually prolong the mission lifetime to produce the data which I'm going to present. And I'd like to thank Chris Martin and Mark Seibert, most especially, for their help in that process. A lot of hard work went into that. And what you can do with the data you collect for all these galaxies here is to use it to fit spectral energy distributions. This is a fitting done with the MAGFIS routine, which is a favorite of Simon Driver. And what we see here is the morphological classifications which we have in GAMA, which are extremely high quality. For galaxies out to 0.06, so local universe, and then you can see the percent for all the galaxies in the whole population. These lines are the sort of percentiles going 10, 20, 30 to the medium and beyond of at every wavelength point that's measured. And then you see beautifully this whole thing again, whereby you have the red galaxy, the ellipticals, red, dead. They've also got very little dust emission, and the young disk-sporty galaxies with a lot of UV emission. And just look at the range of UV emission in there. The level of these curves is placed so that it's at the same stellar mass of each galaxy. I think it's a beautiful diagram, actually. Oh, I had to put this in. I just wanted to say that we did this for 100 galaxies rather than 300,000 about 15 years ago with the ISOFOT project, and I just wanted to put one slide into this talk that we measured with the ISOFOT instrument. But what you can see is that we've got the photometry right. You've got a level of the points in the far infrared compared to the level of the points over here for these morphological types, exactly the same as we now measure in the MODI survey. So if Dietrich Lemke is listening in, we did get it right, Dietrich. Now the problem is, what one can do one problem is actually measuring star formation rates, surprisingly enough. It sounds sort of straightforward, but there's lots of different ways to measure star formation rates. You could actually look in the UV, but if you look in the UV, you've got to correct for dust, and there's all sorts of ways of correcting for dust. You could also look in the infrared. You don't have, then you see, but the trouble is, then you sometimes have optical photons heating the dust. You can do mixtures of all these things, but they all give you different results. And this is characterized in this plot. We've got the whole of the local galaxy population of disks on these plots. So the full volume-limited galaxy population, but morphologically-selected disks. They should be great standard candles for calibrating star formation indicators. And we plotted every star formation indicator versus stellar mass and put a line through it. And you can see on these diagrams, the lines are at different slopes. The scatters are different. Part of the scatter is different because it's physical. In the nebula lines, you're looking at young massive stars, which actually are varying in star formation rate on short timescales. This is radiation transfer with the NUV from Galaxies. And here you have a longer wavelength UV, which is for even heavier stars, more scatter. You've got low scatter in the U-band, somewhat longer. And you know, there is no such thing as a star formation rate, essentially. And then you look here. And the interesting thing is what I want to emphasize is that the energy balance measure, this is MAGFIS, are actually no better than any of the others in terms of systematics. Because energy balance, where you actually use the infrared to make sure you at least keep track of all the photons in the galaxy, these routines rely almost all of them on a fixed attenuation curve. And it doesn't matter if you have a fixed amount of energy, if you have the wrong relative amounts of blue and red photons going into the dust, you will get the wrong star formation rate. And that's partly why those scatter on MAGFIS is high. There's another reason that there's a lot of noise in the data. And we decided to go for the jugular. We were going to look at the UV because we want to look at UV at different timescales, and we decided to actually bite the bullet and correct for the dust. If you're correcting for dust, you need always to have, as I said, variable attenuation curves if you're going to get it right. So we did it via radiation transfer modeling of simple geometries for these things. But you also, which is something which somehow is not yet is been lost, you need to take into account local absorption in star formation regions. And if you do this and work out what happens to the photons and plot what happens to the infrared photons, what you find is that the warm infrared photons, the ones which are sort of short widths of about 70 microns, they're coming from the star formation regions. The long photons coming from the diffuse ISM, and this is physics because the diffuse ISM is the diffuse neutral ISM, predominantly in a galaxy in a local universe like the Milky Way, and the ratio of those two things is basically the fuel within a disk and the stars which are forming out of that fuel. So the 24 are the stars, and this is the diffuse gas. And that color in the infrared, that's what it means physically in galaxies. Now, when you do this analysis, I've plotted here the specific star formation rate, so it's going down, that's star formation rate divided by stellar mass. For our UV observations, uncorrected for dust, and then here corrected for dust. These stars are the more inclined galaxies towards edge-on, and so you see definitely the inclination effects on the attenuation curve being pulled up and corrected here, and also the scatter going down. The acid test of whether you can actually measure a star formation rate is whether you can actually reduce the scatter in this relation. And this is the scatter in that relation. The red is before correction. This is a low mass from our low mass limit of 10 to the 9.5. And this is the high mass. And you see, we've peaked this thing up simply by this radiation transfer analysis. Now, I'm going to measure zeta with gamma. There's two ways of doing it. The first, what we're going to do is to look at the dependence and the amplitude of the disk main sequence. I call it disk main sequence because we've selected a morphological sample of disks in this survey. And so it's not really the same as the other main sequences which I showed you before, because they were color selected. We don't color select, and we don't color select because we want to be totally open to the possibility that we can see red disks, which would and if we weren't, we wouldn't be able to do this analysis. And then we will then look at this curve for different environments, dark matter halo environments. And then the second method is to look at the scatter in the main sequence relation and understand that part of that scatter is due to cosmological effects, due to the fact that a galaxy with a given stellar mass can end up with its given stellar mass after progressing through the sequence of merging parent dark matter halos by a different route. And so if zeta is not -1, not the m halo to the -1, it will end up at its current stellar mass with a different amount of, with a different current star formation rate, causing a scatter in the relation. Now that's work which is still in progress, and I'm not going to talk too much about that. So but I will at the end, but I'll talk mainly about this method for looking at zeta. So here we have it, the first of the final plots. So what I've plotted here is for a so-called field galaxy sample. Now that is a reference sample of galaxies which are not grouped. So that's about most of the galaxies. That's plotted in this red line. And the width of this line is the uncertainty in the mean of that line. And then what I've then done is plotted the grouped centrals and grouped satellites. These are all disks. So we're measuring not chalk against cheese, we're measuring cheese against cheese. And there's two types of group galaxies. There's dominant massive galaxies, which are at the center of a group. They are galaxies which have progressed along the primary branch of the merger tree. And the satellites, which are a result of of a small mass dark matter halo merging into a large mass dark matter halo. This is all in these papers here. And we found that our main result here was for the group centrals that they have identical star formation rates to the field. I mean, I was astonished by this. The typical predicted ratio of dark matter halos for those two populations is about 5. But they've got the same. So at least at this regime of stellar mass, we've got a zeta function which is close to 1. We actually have it minus 1.1, but this is mainly due to the systematics in the merger tree and the deduction of halo accretion rate from that merger tree. And then you can look at the scatter on this plot, and you know, these are the centrals, and these are the field, and then you just have to look up here, and it's straight as a die. This is the galaxy has no idea it's in a group. The satellite's a different story, and I'll come on to that at the end later, but there is an effect on the satellites, and it's clear that this is the high mass group of galaxies, these are low mass galaxies. It looks that there's a sort of bimodal population developing here, although the majority of galaxies, even if they're a satellite, are actually not changed very much in their star formation rate. There's more scatter in it. We checked this with weak lensing analysis. We stacked up all these samples using the VST Kids. Maya was doing that with the VST Kids team. And these two red points are the results. There is actually not actually a statistical difference between them. So in this case, we think there is nevertheless a halo difference because the whole halo dynamical mass has been calibrated by VST Kids. But I had to show that, but on this subclass of galaxies, because there simply aren't very many central galaxies, that's the truth. So you lose statistical precision when you do the stacking. Now, as a byproduct of this, we also had measurement of the star formation, the change in star formation rate at z equals 0.1. These are the three plots, high, medium, low. We were able to do this due to this high position of our analysis. And what one can do is then convert this to how a galaxy is changing its star formation rate in co-moving space, as if you were riding on the galaxy and then measuring its star formation rate since z.1. And what we find is a very steep relation. Low mass galaxies are actually brightening compared to the overall decrease in density of the universe, which is given by this straight line here, whereas the high mass galaxy is going down. Now this is something which was very steep for this, simply because we have a very flat main sequence relation with the way we calibrated it. Of course, in an infinitely flat, completely flat, you would need an infinite star formation rate in order to have the curve moving down. But that's the reason we get a very steep dependence, and this is a problem to explain. So now I'm just going on briefly to the satellites. The satellites, of course, you expect a lot of trouble because they are rotating around in the dark matter halo, orbiting around, and as they do so, they are spinning through the hot gas, which is particularly going to be a problem in the virial supported halos, because then you get the stripping going on, and also the gas being taken out of the immediate circumgalactic halo, and so you expect large effects. As I said, you don't actually see very large effects, and if you look at the histograms, as I told you before, of satellites, it's sort of binodal. And what we found is that there was actually, I skipped this one. What we can do, of course, for the satellites is nevertheless, because we know the mass of each halo the satellite is in, since it's always in a group, we can actually look at the effect of this depressed satellite population. And again, it's completely independent of halo mass. We've not found anything so far which the halo is affecting the star formation of a disk galaxy. And there is, however, one thing which does affect the star formation of a disk galaxy, and that is an AGN. If you then, these plots were without an AGN in the central galaxy, but if you then look at the same sample in the high mass halo bin, where there is an AGN in the central galaxy, it goes down by a factor of 0.5 dex. This is an immediate demonstration of AGN feedback, albeit in a different form to what has been popularly proposed. You can actually check this. You see this, sorry, going backwards and forwards. This is the effect that you see. So it's quite a strong effect. And it looks, these AGNs, they are photon AGNs. So there's some sort of a photon feedback process going on which is affecting the IgM, possibly in very large groups, which is suppressing star formation. Now, back to the scatter in the disk main sequence. I talked about, to finish the talk, I'll just briefly talk about the cosmological component of scatter. I'm nearly through. The point is that we've actually, when we were looking at the group centrals, we were actually only able to look at very massive galaxies and very massive halos. We were not able to look at whether centrals in low mass halos had their star formation rates affected by their group environment. But one way you can do that is actually to consider the effect on the scatter, as I've previously mentioned, of arriving at a point on the main sequence relation through different mergatory routes. And you expect this to, this cosmological component to have long time scales, sort of plotted beyond 10 to the 9 years, which is sort of beyond U-band. But what actually stops you doing that is the feedback cycle on 100 kiloparsec scales of gas coming into galaxies. Remember, the gas coming into galaxies has to be cold to come into the galaxy. You can't, and because of the cooling curve, even if your escape velocity corresponds to 10 to the 4 Kelvin, 10 to the 3 Kelvin, you can't have 10 to the 3 Kelvin gas. So you always have cold clumps of dust, of gas coming into galaxies, and the gas going off in the other direction is always hot because you've got to escape the disk. And because of this quantization of the gas inflow, you expect a flickering as these clumps of dust comes in, and the flickering time scale, and therefore the amplitude in which band will depend on the typical mass scale in the circumgalactic medium, which is accumulating this material. So just to remind you about the scatter, I don't think I need to remind you that we had these, in the NUV, we've had these scatter plots. And the point I want to, this is work which is ongoing, so I'm only able to give you qualitative numbers here, but effectively, in the NUV, and especially the U-band, there's very little room for deviations from our that should be zeta, and there's a zeta missing proportional to m halo to the -1. And so even for those low mass galaxies, the secular growth of the disks seems to be more or less independent of where they are. And you can see this is a plot from the weak lensing analysis showing this plot up there, showing the halo mass versus the stellar mass. So if you look at the 10 to the 9.5, which is our lowest mass galaxies in our sample, you see you're actually, there's going to be a big spread in halo masses here, but you're below the critical mass of 10 to the 12. So even down to where it should be turning over, we don't see any evidence for the turnover. It's not only the global turnover, it is also the fact that the actual feeding of these dark matter halos, the mass rate coming through the real area and all the other processes which are going on and shredding these things up, it gives you a large dispersion in halo mass accretion rate, and the relative dispersion to the number goes up as you go down to lower halo masses. So it becomes especially problematical if you can't detect an increase in scatter as you go down the main sequence relation to lower stellar mass rate and therefore the lower halo masses. So the current state of play is that we've yet to set this in concrete, but it looks as if there's almost no environmental effect on star formation in rotationally supported galaxies anywhere along the main sequence from 10 to the 9.5 up to 10 to the 11. And hardly any effect on satellites apart from AGN. I won't talk about this. This is the topic of flickering of spiral galaxies due to the quantization of the Gaussian flow. I'll just round off the talk by giving a summary, and I couldn't help plotting this old plot we did with Alessandro Borzelli from our preparations for the Virgo observations with ISO. I remember talking to Alessandro and saying, why is that so tight? And neither of us can answer the question. We hope in the future, or maybe the reasonably near future, maybe to be able to say something a little more about this. But basically, spiral capital's are tending towards, if you select them morphologically, and they're really isolated, in other words, not interacting, they are tendentially becoming some sort of a standard candle. And the direction of this research in the future will be to use that in order to look at some of the bigger physics problems that astronomy can help to answer, such as gravitation, dark energy. I won't spell these out. These are all the things I've just been talking about for the last half hour. Once again, thank you, everybody, and I look forward to a good few years working here still. Thank you.
So, thank you, Richard, for this very nice overview of what drives star formation in galaxies and what it does not depend on, which is indeed a puzzle. There will be questions. Who would like to start with the first question? Yes, at the very top. Let me put in more light.
When you're talking about breaking this independence for the satellites with AGN, how are you selecting the AGN?
These are by the optical spectracles, the 003, H alpha N2. So we try to avoid known pitfalls like liners. We try to we look at all the spectra. There are enough of them there. But I take the point. It is a problem that classification could be problematical. Yeah.
Over there, Sasha.
I had a question about the spiral galaxies that are the central galaxies of those more massive halos. So if I understood it well, there are actually very few of those.
There are very few of them, yes. That's the point.
So
there are very few of them.
Yeah, so wouldn't it be fair to say that it's not, the puzzle is not how come they are making stars in the same way that field galaxies are, but why are there spiral galaxies as the centers of those halos? I mean, if they're so special, is there maybe something that makes...
Well, yes. I mean, this is an active area. The relation, basically the angular momentum transport in halo merging tree structures, and also the effect of minor mergers. I don't. The fraction is indeed very small, very high masses of order 10%. So I can't answer that. I'm presuming there is a path for 10% that preserves a coherent angular momentum at the center of the halo.
But so what I was trying to say is that maybe, since they are apparently difficult to make as such in this environment, it's difficult to say that they do the normal thing, which is they are independent of the environment.
Well, I mean, there is a very clear distinction between being in the blue sequence in that population and being off it. And so I think this is a good point. One needs also to do a similar tight analysis involving the spheroidals in order to really answer, and that's something which we have not yet done. But this is a good point. We would need to do that. We need to look at the spheroidals and show equally that they're not forming stars anywhere. If I'm going to really be able to make the point that galaxy morphology is the main thing here.
So, and the other question, if I may?
Thank you very much for the very interesting talk. You mentioned a slide where you...
Wait, we have a microphone. I come back to you, Sasha.
Thank you very much for your very interesting talk. In the first slides, you explained the theta mass function with the parameters tau and kappa and so on, and including your explanation, you concluded that the star formation ratio is independent of environment by exponential growth. And here you you said the secular growth is equal to independent of the environment. And in the last statement, you made the conclusion that the galaxies is determined by morphological mix rather than gas filling. What do you mean by morphological? Is this the intrinsic problem you have? And is there a connection to the AGN?
Yes, well, I mean, there's obviously an observational connection to AGN in the sense that mass of black holes is very, very strongly coupled to mass of spheroids surrounding the black holes in either bulges or fully spheroidal galaxies. But what I mean is that whatever is going on in the process of when a parcel of gas gets down into the galaxy, if it's not rotationally supported, if it has to be pressure supported, then it has to get to a high temperature and it may not form stars so easily. Whereas if you have a rotational disk, you have a large area where you can spread a lot of energy flow and still allow gas to come in. So there's a sort of physical intuition, I'm just talking about intuition now, which might explain why you should expect star formation in disks and not spheroids. But fundamentally, this has to be done observationally, and we have yet to do this because, as I just answered, we need to look equally well at what's going on in the spheroids as a function of all these environments. I don't know if I've answered your question, actually.
That's correct. And what do you mean morphological?
I mean, rotationally supported versus pressure supported. So the stellar system in a spheroid is randomized in its velocity vectors, whereas in a disk, it is mainly got a single angular momentum vector direction, and the gas also has it because the stars are forming out of the gas. And therefore the gas is also rotationally supported, even though for most of those objects we only see the stars.
So can I also intersect a question? When you talk about the environment, does this include major mergers? I mean, we noticed when we do a sequence of minor merger events that, yes, the gas was reconfigured, and yes, it looked differently morphologically. However, the star formation rate did not go up, meaning that, you know, whatever was locally unstable remained locally unstable, and the global messing up did not matter much. Different for a major merger where you really screw.
What we see, that we have, that's a major line of observational, is to look at mergers in gamma. What we see is strong dependence, strong fluctuations in star formation, but very short recovery time scales to get back to the equilibrium. Yes. And the reason those time scales are short is because this tau resonance, this T resonance time against wind loss, is actually quite small. And so what this actually tells you, in the work which is being done in gamma, is that winds are very important. And there's a rapid circulation of gas in and out of the galaxy going on. And the process seems to be robust, so even when you hit it with a hammer, like a major merger, at least if there's still a disk afterwards, it will quickly recover its star formation. Aaron Rowbottom and his papers are looking at that, and Luke Davis.
So, further questions? Sasha? No. Good. Before we thank the speaker again, let me announce next week's speaker, Patrick Enebel from the CEA in Saclay near Paris. He will talk about much smaller scales, the stellar initial mass function, and how we can understand its seemingly universality in the at least local universe. So Richard works at the Max Planck Institute for Nuclear Physics, so there will be no joint dinner afterwards because he's a local speaker. If you want to continue the discussion, you know where to find him. So let's thank again Richard for this very nice talk.